Anyone listen to radio this morning? You don't listen to radio, do you? Do you? Weren't they talking about it on the radio? 9/11? On the 18th anniversary of 9/11 on these notes. I started the notes. All right, anyway. Yeah. Huh? All right, fourth hour, 2000. What year is this? 19? I shouldn't do that because I'll probably use this video for 10 years. And then, that's a 10-year-old video? Anyway. Okay, I decided to teach transformations. Can everyone say transformations? This way. How I showed you the notes yesterday. So, be better than first hour. That's right, first hour. I put you on the spot. I had to get the calculator out because I would ask, what's 2 plus 2? And they were like, F you, Mr. S. We ain't answering your questions. All right? Because they wouldn't. They wouldn't. Nothing. That's another thing that was different back in the day. Before 9/11, all the kids answered questions when the teacher asked. All right? And now it's nothing. Nothing. So I sit here like a loser. Hey, class, what should I plug in this question right here? And what's the answer? What should I plug in? 3. Okay, now I'll tell you why when you plug in 3. And by the way, class, think about it. Okay, don't answer the question yet. What happens when you plug in 3? What's your output answer? Shh. 5, 4, 3, 2, 1. Go. Oh, no, they didn't answer. First hour. 4. Maybe didn't understand the question. Okay, now here's why I did this. And then I'll show you what I have online that you can use as an aid to looking at transformations a different way. What you got to understand is you have a squared, which is a what? A picture of a what? Say it. Parabola. And the most important point is a what? The what? Vertex. So when I showed you what you did yesterday, we actually just found the what? We found the vertex. So now what we know, 1, 2, 3, comma 1, 2, 3, 4, we know 2 of the transformations. And what does it mean, transformations? What did I do to this graph to make this new one? What are the changes? Well, it moved 3 to the right and what? Up 4. And I'm not going to put them in a particular order. We'll just put them as we discover them. That's what I call this, a discovery. And that's really the best way to do this. And then we can do some other points. Now that I know this is the vertex, I'm going to try to find where these 2 points go. And where that would be is by plugging in the next 2 x coordinates right by 3. All right? And then we'll do that offline. Take a little break. Okay, so we calculated these other values, and we should have known that 4 would have got you a 6 as well. Oh, very shaky on this emotional day. All right, now, hard to write on this slippery screen. So that's a really shaky, ugly parabola. All right, and then you don't see this because my scale on my coordinate plane to the right is different than the one on the left. But what would you say that parabola is compared to the other one on the left? Skinnier or wider? Now, we're not going to use that word ever again. What we're going to understand is this 2, what did it do? Did it stretch it or shrink it? Stretched it what, though? Because today we have a different way of stretching it. Stretching it vertically or horizontally? And the answer is vertically. I'm sorry for my scratching writing. And I'm just going to shorthand it. Stretched vertically by a factor of 2. I am not writing the word factor anymore. I can't even write it. I can't even spell. Very emotional. And then I think that's it. So I should have just sort of put a period. And then at the end of all these, this has nothing to do with transformations, but it does affect the domain and range sometimes. Did it affect the domain? Yes or no? Did it affect the range? What's the range? What do I put on 4? Because we've been screwing this up. It's included, so that includes or has a bracket. The perspective of what are the transformations, it's always based off of the parent. That's why we're playing parent-child. See that? Parent-child. Parent columns on the left, child columns on the right. Here's another parent, and then a child. Isn't it cute? Okay, so the first thing, I had someone 7th hour have a problem with this. They weren't recognizing what is their function that they're dealing with. All right, and it's a cubic. So it should be compared to this. And before I do anything with this, what we're trying to understand is, where is the new most important point? And the most important point for a cubic is what I call this point of inflection right here. This little, where the graph kind of just does that little bloop. I don't know what else to, say about that. So where do we find that? When we plug in what? What are we going to plug in? That's what I showed you yesterday. It's really a smart way to approach this. Then it takes care of the right, left, up, down moves. When I plug in -1, what do I get? You should understand it's -2 right away because I don't know where that negative, I saw it. This thing likes to do screwy things on me here. -2 for y. So -1 comma -2. And then we're going to see that little whoop at that point. So that's what the point of doing this is. So what should I plug in next? Don't say 0 and -2. I want this to work out a little better. So I decided to plug in 1, and then I could go back and figure out what I plug in. Why did I do that? What's 1 plus 1? What's 2 cubed? What's -1/2 of 8? What's -4 minus 2? And if you can't do these calculations, like a rabid dog, I should come by you, because you should be able to be numerically capable in this class to do those evaluations. Input, you say it. Okay, 1 comma 1, 2, 3, 4, 5. Oh, something special happened here. Then I'll go back and I'll plug in 0. Plugging in 0 just gives me -1/2 minus 2. What's -1/2 minus 2? -2 and a half. So 0 doesn't give me this value that's 1 rise 1. It gives me a value that's only a half below that. And we obviously have a flip. Don't we have a flip across the x-axis? This is why it's... All right? So what is that? Is that a vertical stretch or a shrink? Shrink. So we'll put that down later, and then we'll put the reflection. Probably jumping ahead of myself. And then I think I put -3 as a value in the other hour just to get a nice little... -3 plus 1 is -2, but -2 cubed is -8. -8 times -1/2 is 4. What's 4 minus 2? 1, 2, 3, 2. So you better get at least a reasonable x cubed if you do what I'm doing, which is plug in some points. It better look like a classic x cubed picture. Now again, the only thing that's bad about my notes is the scaling. You can't really see that this is vertically shrunk. It would look wider. This one would look skinnier, the previous one. We don't really see that because of my scale, and I think you should be able to get that. So it's 1 right, 2 down, x-axis reflection. This is in no particular order. I'm just getting all the things down. And what was the last thing? Sorry. Oh, yeah, vertically sharp. Sorry, my mind went blank there. Vertically shrunk by a factor of a half. Don't say a -1/2. Where's the negative? Did I make a mistake? It's 1 left. I got 9/11 on my brain. Okay, I can't think. 1 left. Correct? Okay, sorry about that. 1 left, 2 down. And then x-axis reflection, vertical. And then what's the domain and range? What's the domain and range? I lost my. It's all real numbers. Don't do as I say it, not as I do. Don't ever do this. This is lazy. Both of them. Okay. All right, here we go. Shh. 4th hour. It's mutiny. All right. Okay. Now I decided to do this because yesterday. Okay, don't call it unfair, but I did say number 7 yesterday was not like any others. You just had to try to recall from last year or the year before. It wasn't done in transformations. So I'll zoom in on this if this allows me. Now I gave you a rational expression in transformational format. Okay, so let's try to guess. What do you think the -1 would do? The negative. What do you think instead of 1 on the top? -1. Flip over the... Oh, it's actually x-axis. I do like that, though. That would have to be on the bottom if it was. And then what do you think the minus 5 does? What does that make that move? It is 5 right. And I don't know if everyone said that. Let's think about it. What can't I plug in for x? Say it. That means there is a vertical asymptote, 1, 2, 3, 4, 5, at 5. So that proves that this got moved 5 right, because the vertical asymptote is at x equals 0. So this wouldn't have worked on number 7 yesterday, because number 7 was not in transformational format. It was just a couple binomials divided by a couple binomials, and you can't look at it the way this is done. And then what do you think the plus 3 does? Moves what up 3, though? Here, I'll give you a hint. Moves what up 3? The horizontal asymptote. I'll prove it. It goes back to what is an end behavior asymptote, and it's about plugging in a million. So let's analyze what happens when I plug in a million for x. What's negative 1 over a million? Minus 5. What is it essentially? 0 plus 3, though. What's 0 plus 3? 3. You are going to approach 3 as a y value as you plug in bigger and bigger x's or smaller and smaller x's. All right, then I annoyed my students the other hour, and I'm going to annoy you. How do I find the y-intercept, which I'm going to put right up here? How do you find the y-intercept, which is the easier of the two things? Plug in 0 for x. What's negative 1 plus 0 minus 5? I'm sorry, divided by 0 minus 5. Plus 3. What does that end up becoming? 3 1/5. So the y-intercept is 0, 3 1/5, which actually tells me 0, 3 1/5 where this graph exists compared to the left side of the vertical asymptote. It is right here. And then it approaches these asymptotes without crossing. And guess what there is then if the other graph should be down here? There's actually a what? There is an x-intercept. How do you find an x-intercept? I'm going to annoy you. You plug in 0 for y, and it's not beyond the capabilities of this class to figure out what the x-intercept is, because guess what? I actually taught you how to solve this. We actually had this in the chapter AP chapter, right? What do I do next, everybody? Subtract 3, and then we didn't have a question like this, so I'm going to make it subtract 3 and make it 3 over 1, because actually this is fraction equals fraction, which always allows you to do what? Cross multiply. And then you could distribute as you cross multiply, because this is cat, me, yow. And then it's 1 times negative 1, which is negative 1 on the other side. And then you can subtract 15 and then divide by negative 3. All right, you know what? That 3 goes into 15, right? 5 times. So this is 5 1/3, right? 16 thirds would be 5 1/3. And I want to know it that way because here's 5, then here's 5 1/3. And that tells me, yes, I was right. I'm so hungry. Can't wait to eat my lunch. Okay, so now we can see this in a transformational format. It went 5 right, that's what the minus 5 did. 3 up, that's what the 3 did when it's in this format. It was, look, this graph is here, now it's down here. So it was reflected. I was about to say flipped. I'll take flipped. Reflected sounds more like a math word, though. Reflected over the x-axis. Sorry for giving you the shorthand. And then is there anything else? No. Okay, and then it definitely changed the domain. What can't x equal now? Not 0, but 5. And then what's the range? Not 0, but 3. And hopefully you understand that as I press pause. Okay. Now that we have all these things, I gave the students a part of, I'm going to go to my calendar, I think. Ah! That's your pictures online. Okay, hold on. That's a mistake. Okay, I got to press pause on the video. Get sued. All right. So I'm gonna go ahead and go to the calendar and just give you. Is this the right calendar? What class is this? Okay. Oh, there it is, September 11th. All right. Look at. I stole it from the internet. I almost put stolen from the internet on this. Transformation notes from the internet, and then I think it's. Nope, that's not it. That's not it. Okay, let's go back. But it is from that college, Modesto Junior College, this teacher. So I think I did hit it. Children over there, stop playing whatever you're doing. I have two little kids there fighting each other. Okay. Why is it not hitting? Do you see what I see here? This is a stunning video. What? Oh my gosh. Okay. Shh. And then I thought this was a great, it's 10 pages long, but it's something for you to read. And it describes all the transformations, horizontal transformations, all right? And then reflections, both x and y axis. See that? When the negative is on the inside, whoever said vertical or like a x-axis reflection, it's actually on the inside that reflects it over the y-axis. And we're going to have one that has that happen. Vertical stretching and shrink. Oh no, horizontal stretching and shrinking. And that's why I'm covering this right now, because our next one has a horizontal stretch or shrink. But they really describe it perfectly. And then graph fumble through doing their changes from what they see in the equation. I'm doing it a little different, where we find like the critical points, and then we can go ahead and say what the moves are after that. All right, but then just to give it props, what I just handed out to you, and feel free to read this on your own, it's awesome, is this. Don't you recognize that? Please stop that. Seriously? Do you see that? That's what you have in front of you. Now, really focus on the very bottom, the bottom two things. Of course, when you have a multiplier on the outside, like our first example, it stretched it vertically. But when you have a multiplier on the inside, that's said to be a horizontal stretching or shrinking. And that's why I gave you the cheat sheet specifically for this question that I have here, that this is not letting me move. There we go, finally. This one. And obviously you can see that you have the square root function. So what's the most important point in the square root function? Where 0, 0 ends up, right? Okay, so back to focus. And then I'll zoom in on this, and then we'll talk about the transformations after. So there's the question. Give you a second to write it. What point should I plug in? Right away. It's -5 if you trained from yesterday. And then I'll put a couple more in here. It's -5 because -5 plus 5 is 0. 0 times 4 is still 0. Square root of 0 is 0. -0 minus 2 is -2. And you know what that point is? -1, 2, 3, 4, 5. -2. It is where that critical point for a square root function ended up. It is that one. And that's the point of me saying plug in that specific value for all of these. All right? And then we can go from there. And then we can analyze the other stuff. Now, what I did with the other hour is, first of all, can I plug in -6? Can I plug in -6? No, because then I get a negative in the square root, and that doesn't graph on a real coordinate plane. That's an I number. So fumble. -6 is an I number. So what I can plug in is -4. And -4 does work out nicely. When I plug in fumble, now we're just going to fumble on purpose. Let's hear him say fumble. All right. -4 plus 5 is 1. 1 times 4 is 4. What's the square root of 4, everybody? 2. What's -2 minus 2? Oh, no. So we have -1, 2, 3, 4, comma, 1, 2, 3. Something weird has occurred. And actually what you should understand is I can plug in -3, -2, -1, and I could find the Y-intercept, but that's not really the point. What I wanted to find was where does the graph do its nature? Where does it do its, its natural look? And those 2 points tell me exactly what happened. As a matter of fact, this point is where this point ended up. And this is why I want to express this the right way. That 4 multiplier is on the inside of the function. So hopefully I have this ready on the internet. The thing that I've copied for you. Boom shakalaka. I can't write on this, but that means it is the very last condition, and that's how you have to express the transformation. What's 4? Is it between 0 and 1, or is it greater than 1? Greater than 1. So that represents a, what does that say right on your sheet? Horizontal shrinking. What does shrinking mean? Let's think about vertical. What does shrinking mean? Doesn't it pull it towards the x-axis? And then it'll allot it like a parabola, makes it look wider? And then vertical stretching pushes it away, correct? So what's horizontal shrinking do? Pull it towards or push away? Pull it towards. As a Federer act, that point, if I pulled it towards, this is that graph. Like that's what that point is. Because look, this is 1 then 1. Whereas this goes 1 and then it's 2 away. That means that's what the picture would look like, but now it's reflected and moved. Do you understand that? And look at the picture, it's pulled what? Towards the y-axis. So I'm going to write this down right now. It is a horizontal shrink. That's why I like this thing. By a factor of, I told you I'm not writing by a factor of, and you do say 4. Don't do the square rooting of it. All right? You know, that it's just you say by the number that is actually inserted that's different when it wasn't there before. Then we can do the other things. It's an x-axis reflection. Oh, I like saying it that way. X-axis reflection, and then the moves. Reflection, and then 5 left. And then at this point, I didn't say this, 2 down. You should start figuring out that x plus 5 on the inside plus 5 goes 5 left. Probably the opposite that you would think. Plus is a right direction on the x-axis. You think opposite. But then minus 2 is down, and that's what you would expect. So I've always told my students for the right-left shifts, think opposites. And then for the up-downs, think same. X minus 5, wrong color, right? But that's 5 rights. Plus 3 again was 3 up. What I would expect. Do you remember this? Opposite, same. Okay, so this discovery actually proves it as well. Now let's make this go fast. Well, not really. Okay, because I'm going to be annoying again and make you... And I had a great question first hour, even though I insulted them in the beginning of this, didn't I? That's because they wouldn't answer any questions. Nothing. But one person did ask a great question. Wouldn't that be like a vertical or a vertical... dilation is the word. Stretch or shrink. If I change 2 to 3 or 4 or 5. And we're going to talk about graphing exponentials in Chapter 3. They are actually technically right. When you change the base, it does change the steepness of the graph. But you don't call that a vertical dilation. You could have this. This is how I answered her question. 2 raised to the 3 minus x plus 4. And then you have a big fat multiplier out in front, like by 4, with 4 not being part of that. Don't write this down, just look. That is a vertical stretch by a factor of 4. You get it? Okay, and I did want to cover her question as far as what that is. And I don't like when they do that with exponentials, but we probably will when it comes to it. But here's really fumble. Do you see that? Here's what I want to do. Did you know that this is the same as pulling out a negative 1? And then it's x minus 3. And then did you know that 2 to the negative first is a half? So the graph of this is exactly the same as the graph of that? Absolutely. Isn't 2 to the negative first 1/2, everybody? So where did the negative 1 go? Well, now it's just 1/2 raised to the positive first. And then x minus 3. So... what number should we plug in regardless first? I have no idea what just happened there. I did not close anything. I'm just, oh my gosh. I just love this computer. Okay, I guess it wasn't that big of a deal. All right, and I didn't mean to erase that. This is great video stuff. Let's go back to the original. What should I plug in for x, everybody? 3. I'm not writing it down anymore. I'm not doing a chart. What's 3 minus 3? What's 2 to the 0 power, though? What's 1 plus 4? So 3, comma 1, 2, 3, 4, 5. Fine, I'll write it. 3, comma, and then 2 to the 0 plus 1, or 4. 1 plus 4 is 5. And you know what that is? You're understanding that the parent function, this is the most important point to know. Where did that point go? Where is that 0, comma 1 point? Because that's where the asymptote's very close, and then after the other side is where it starts taking off in a direction. So, what is the asymptote? Where is that asymptote? This one's at y equals 0. You should know from what we see up here where the asymptote got moved to. Starts with an F, and it's in the equation. It's a 4, everybody, because that got moved up 4, and we can prove it by one more plug-in. Let's go 4 for x. 3 minus 4 is negative 1. What's 2 to the negative first? 1/2. What's 1/2 plus 4? 4.5. And what's going to happen as I plug in 5, 6, 7? What are these going to become but never quite make it to? 4. You're never going to get to 4. You're going to get 4 point something no matter how big you put in those numbers. That's thinking. That's not being a robot. And what happens with this particular graph, and where do I put the stuff? All right? 2. 3 minus 2 is 1. 2 to the first is 2. 2 plus 4 is 6. And then you should see, as I plug these numbers in, you start getting bigger things there. So 2 comma 6, whereas these start going here, you have a flip over the y-axis. That's what you have. Look at that graph right there. So that's when I said this is the same as 2 to the negative first times x minus 3 plus 4. That negative 1 inside the exponent is a y-axis reflection in relation to the parent. All of these terms are what happens to the parent. How is this transformed? And that's what the whole idea of this section is. So that's what we got to say. And then it is 3 right and 4 up. And then the domain is all real numbers. Hey, I have a question. What's the range? What do I have on 4? Oh, I heard whoa, brackets over here, parentheses over here. Braveheart, fight. It's parentheses. Why? It's never going to get to what? That's what the vertical asymptote. What? That's what the horizontal asymptote. I even gave props at the bottom of this. These notes were used as a discovery for transformations. The website, College Notes, shared on my calendar, describes them magnificently. And for those that go above and beyond the call of duty, we'll actually read those and get some real sensical information. All right, but what should I plug in first? What should I plug in? Negative 3, and what do I get as an output value? Nope. Negative 4. And what that describes is 1, 2, 3, comma 1, 2, 3, 4. This describes where the most crucial point of the graph, the vertex, if you will, I guess we could call it, where it ends up. That's the vertex. Then what am I going to plug in next? Probably not negative 2. I'm going to probably plug in 1. What's 1 plus 3? 4. What's negative 1/4 of 4? Negative 1. What's negative 1 minus 4? Negative 5. 1. Negative 1, 2, 3, 4, 5. Whoa. What would you describe that as? Wider or skinnier? Wider. Then the other one is, why am I picking negative 7 and 1? I'm trying to get a nice number that works with 1/4. You're not stuck with what you plug in. And I know negative 7 plus 3 is negative 4. But to absolute value it, you get 4. 4 times negative 4th is back to that negative 1 minus 4. It's this reflected point over here. That is definitely a wider. So what do we say about that 1/4? It is vertically stretched or shrunk? Shrunk. When you're pulled towards an axis, you're pulled towards it. Okay, so you're shrunk towards it. Stretched is push away. All right, so shrunk by 1/4. It's x-axis reflection. Everyone putting their books away. What time is it? Ah! 3 left, 4 down. And then domain, all reals. Range, negative infinity all the way up to -4. What do I put on that? Bracket. Shut her down.